Good morning to everyone in Mexico City and good afternoon, Dr. Getro Medicus.
Hello, nice to meet you.
Me too, nice to meet you. Welcome everyone to this lecture. For those who wish to listen to the conference in Spanish, we have a simultaneous translation option for this event. So the corresponding option is located at the bottom of your screen. I thank Mr. Martín Muédano for his participation and translator for this event. Para aquellos que quieran escuchar la conferencia en español.
For those of you who want to listen the conference in Spanish, we have a simultaneous interpretation for this event. And you can find an icon in the bottom of your screen. And I thank Mr. Martín Muédano for his participation as the interpreter of this event.
Roberto Avelar, Chairman of the Board of Directors of the Mexican Society for Geotechnical Engineering, to whom I ask for a few words of welcome. Please, Roberto.
Thank you very much. Muy buenos días tengan todos los presentes. Me comunicaré en el idioma inglés.
Thank you. Good morning. I will continue in English.
Good afternoon in Austria. Welcome everyone to this important event for the Mexican Society for Geotechnical Engineering. I appreciate the presence of Dr. Gertrude Medicus, who honors us by giving this interesting lecture related to soil constitutive models. Thank you very much, Dr. Gertrude Medicus, for being with us this day. At this moment, we will be connected about 80 people. Thanks to the organization of Ricardo Ortiz Hermosillo, Vice President of the Board of the Directors of the Mexican Society for Geotechnical Engineering, whom we thank for giving this magnificent opportunity to take advantage of the knowledge that a widely recognized international personality in the field of geotechnics will kindly share with us. The professional career of Dr. Gertrude Medicus focus on research in computational geotechnics. It is extraordinary, which will be mentioned later. Everyone is welcome. Let's enjoy this interesting lecture. And again, thank you very much, Dr. Gertrude Medicus, by your presence.
Thank you.
Thank you, Roberto. Next, I am going to read a summarized profile for our lecturer. Gertrude Medicus is a geotechnical engineer with research interest in computational geotechnics. She studied civil engineering at the University of Innsbruck, Austria, and 1 year at NTNU Trondheim, Norway. Within her PhD thesis, she further developed the constitutive model Barodessy and introduced a formulation for clay. Since 2014, Gertrude works as a postdoc researcher at the Department of Geotechnical and Tunnel Engineering at the University of Innsbruck. Currently, she is the PI of the research project Reloading in Barodessy. Her research focuses on constitutive models of soils, in particular on the models Barodessy and hypoplasticity. Her investigations are related to asymptotic soil behavior, stress latency relations, plane strength predictions, second-order work, strength reduction analysis, and small strain approaches. Within her work, Gertrude aims to contribute to the understanding of soil modeling by developing, applying, and teaching constitutive models. I welcome and thanks Dr. Gertrude Medicus for her support to the Mexican Society for Geotechnical Engineering with the lecture, The Use of Visualizations for Teaching Soil Constitutive Models. Thank you very much, Dr. Medicus. You can start now with your lecture.
Thank you very much. I just share the screen. I hope that works now. Thank you very much for your introduction, and thanks a lot for your invitation. I will now talk about how visualizations can help to understand soil constitutive modeling. And before I will show the visualizations, I will just give a short introduction to the topic. Why do we need constitutive models and why do we need to understand them? We certainly need constitutive models if we carry out finite element simulations, and we need to understand the model in order to choose an appropriate model and in order to interpret the results. In addition, constitutive models are also theories which include certain mechanical and mathematical concepts. And to understand these concepts can also help to understand and explain soil mechanics. Constitutive models are therefore frameworks which provide the possibility for further understanding. There are many important aspects related to teaching and learning constitutive models. Amongst others, one has to carry out computations in order to understand the equations. It's important to get explanations and it's important to have discussions. There are fantastic books related to constitutive modeling, and of course there are university courses and videos available. And there's definitely a lot more. In this presentation, I will hardly talk about the issues above, because I will only or almost only show visualizations and animations as one possibility to improve the visual aspect of teaching soil constitutive modeling. The project I'm talking about is an ongoing project. I will therefore not present a complete and finished project. I just picked certain topics related to yield and failure surfaces and different constitutive models. And within these topics, I choose and explain certain included concepts. This presentation should then give an overview about the project, and I want to address two perspectives. That is, of course, the learning perspective. I will give some explanations, and that is the teaching perspective. I want you to get an overview what can be used from this project. Because the whole idea behind this project is to share the visualizations as teaching and learning material with everyone. All those visualizations are shared under the open CC BY license. That means you can basically do everything with it unless you keep the logo and the name there. I will now give a short introduction on stress measures and stress invariance. In a whole presentation, stresses are considered positive in compression. And we often use principal stresses to characterize a certain stress state in geotechnical problems. And if we then also only consider axisymmetric stress state, it is sufficient to display stresses in PQ, mean effective stress, deviatoric stress plane. The red line is, for example, Mohr-Coulomb failure line with zero cohesion. And I show an example of a stress path of an conventional drained triaxial test of rather loose sand. I will a bit later show corresponding stress strain curves and volumetric response. This is just for the introduction here. If I continue to just consider principal stresses, then we can display general stress state in three-dimensional principal stress space. On this slide, I show Mohr-Coulomb hexagon in principal stress space. The blue line is the hydrostatic axis, which includes the mean effective stress of a certain stress state, that is the red bullet here. And the distance of this red stress state to the hydrostatic axis can be described by the deviatoric stress. Now I let the hexagon rotate towards the deviatoric plane if we look in the direction of the hydrostatic axis. And in order to define the location of this red bullet, of this arbitrary stress state, we need a third stress invariant or stress measure. and that can be the loader angle. In this presentation, I use the following definition of the loader angle. That is, and stop here, for triaxial axisymmetric compressions, the loader angle is chosen to 30 degrees, and for triaxial axisymmetric extension, the loader angle is minus 30 degrees. So we have the one possibility for three stress invariants, that is the mean effective stress, the deviatoric stress, and in the deviatoric plane, the loader angle. One disadvantage of the animations is that I choose where you have to put the focus. I choose where you have to look. And maybe you would be interested in looking at another direction of the Mohr-Coulomb hexagon. And that's why I recently started making interactive graphics. Here I again show Mohr-Coulomb hexagon, and you can zoom in, zoom out, and you can turn it yourself. You can turn yourself towards, for example, the deviatoric plane. And here I added PQ plane for triaxial axisymmetric compression states. And you can again turn yourself, for example, towards the deviatoric plane or wherever you want. In this plot, I added cohesion to the Mohr-Coulomb hexagon, which results in a shift of the hexagon. Adding a cohesion allows certain tensile stresses and also allows plane stress predictions. And that's what we can see here, where the solid and transparent part of the hexagon meet. That's how plane stress prediction would look for Mohr-Coulomb hexagon, including cohesion. I will continue to show more yield surfaces, and I will also show more of these interactive plots. Here I want to mention that all of these interactive plots have been created with the software Asymptote. Asymptote is a free software, very useful for creating diagrams and very nice for creating 3D figures. And talking about Asymptote, I want to thank Hans-Peter Schröcker, a mathematician, for suggesting to use this software because it is very suitable for creating these kind of figures. And I hope also for understanding shapes and even a bit later, a bit more complex shapes of 3D surfaces. And just an additional note on this whole presentation, after the lecture, it will be possible for you to download or to have the PDF handout of this presentation. So you can click through the links yourself. And in addition, you can find all the visualizations online anyway. Here I show the yield surface according to von Mises. The cylindrical shape implies that strength is independent of mean effective stress. If I increase mean effective stress, I still get a constant shear strength. The von Mises criterion is used mainly to describe yielding of metals. And again, you can have a look how plane stress predictions would result from the von Mises yield surface. A bit similar to that is Tresca yield condition, whose intersection with the deviatoric plane is a regular hexagon. Again, we can see that an increase in mean effective stress does not affect strength predictions, at least not for a constant loader angle. And again, you can have a look where the transparent part meets the solid part, how plane stress predictions would look for Tresca yield condition. And that's different to those surfaces to describe strengths of frictional materials. As I started with Mohr-Coulomb, And here I show Drucker-Braga with a circular shape in the deviatoric plane. And it's again visible that an increase in mean effective stress results in an increase of deviatoric strength. And again, adding a cohesion results in a shift of the Drucker-Braga towards the tensile stresses. On the next slide, or on this slide, I show the cone according to Matsuoka Nakai. On the website and also linked in the handout, you can have a look at the same animation as just shown for Mont-Colomb and even a bit longer. I again added PQ plane and cohesion, and I also show how plane stress predictions would look for Matsuoka Nakai. And probably you could already see that the shapes of Matsuoka Nakai and Mont-Colomb, that they differ. And to better estimate how much they differ, it helps to plot them in one diagram here on the left. Blue is again Mont-Colomb hexagon and red Matsuoka Nakai. On the left, on the left, I show the difference between Matsuoka Nakai and Mont-Colomb by comparing the mobilized friction angles for different loader angles. Here for a loader angle, for a friction angle of 30 degrees and zero cohesion, or for zero cohesion, the predictions for triaxial axisymmetric extension and triaxial axisymmetric compression, they coincide. I start here the animation at triaxial axisymmetric extension and slowly increase the loader angle. And we can see that the difference in mobilized friction angle increases up to around 17%. And we can see that somewhere between 0 and 15 degrees, the difference is highest. And then as this bullet further approaches axisymmetric triaxial compression states, the strength predictions coincide again. The range of loader angles somewhere between 0 and 15 degrees is exactly the range where plane strain failure is reported to occur. And as geotechnical problems are often idealized under plane strain conditions, it's definitely worth to have a focus in that range if you investigate a constitutive model. I hope you can still hear me. It's pouring outside and it's quite loud, but I hope it still works. This is the normalized deviatoric plane with experimental data of critical stress states of reconstituted San Francisco Baymont. Again, in blue, I show Mont-Colomb, and I fitted the experimental data with Matsuoka Nakai and chose the friction angle of Mont-Colomb in order that axisymmetric compression and extension states coincide. And doing that, Mont-Colomb predictions are conservative compared with Matsuoka Nakai and compared with the experiments. Here I again show PQ plane with a failure line according to Mont-Colomb or Matsuoka Nakai for axisymmetric compression state described through zero cohesion, and in that case a friction angle of 40 degrees. I will now keep this red bullet, this stress state fixed at 100 kilo P equal to 100 kilopascal, and I will increase cohesion and reduce friction angle. And that results in an increase in strength predictions for lower stresses and a decrease in strength predictions for higher stresses. And that's probably what every one of you just expected to happen. I will now just repeat the same here at the left. I will keep this axisymmetric compression state fixed, and I display the deviatoric planes for 100 kilopascal, and in the middle added Matsuoka Nakai, and on the right I added more Coulomb. And I will continue, I will increase the cohesion and reduce the friction angle. And if we now look on the deviatoric planes, we see that this also affects the strength prediction for all deviatoric direction except axisymmetric compression. And eventually, Matsuoka Nakai for zero friction angle and constant cohesion will turn into Mises, and more Coulomb will turn into Tresca for zero friction angle. So it is important to keep in mind that the cohesion affects the shape of failure surfaces in the deviatoric plane, even though strength for axisymmetric triaxial compression is kept constant in this animation here. So far, I haven't talked about a single constitutive model, but only about yield or failure surfaces, which are often included in soil models. I now start with the linear elastic perfectly plastic model, including the failure surface or failure line according to more Coulomb. Here on the left, this is the figure I already showed, the PQ plane with a more Coulomb failure line and the stress path of initially loose Hostan's sample, and it approaches the critical state line. Here above right, I show the stress strain response, the deviatoric stress over axial strain, and below I show the volumetric response of the experiment. I add the simulation with the model, and we can see, we prescribe the stress path, and we can see that the strength is described through the more Coulomb failure line, and I tried to fit the initial stiffness with the elastic modulus, and I tried to adjust the Poisson ratio to get an okay response of the volumetric response. I now increase the initial mean effective stress from 100 to 200 kilopascal, and we can see here exactly what we want, that an increase in mean effective stress results in an increase in strength, and that's what we can see in both figures above. We can also see that an increase in stress level does not result, keeps the stiffness constant. That does not result in an increase of stiffness. And if I further increase the stress level, the initial stress level to 300 kilopascal, we basically see what we just saw. We get an increase in strength, but not an increase in stiffness. Here I add experimental results of Hostan's, and we can clearly see that an increase in stress level should also result, or in an experiment, it results in an increase in stiffness, and that cannot be captured with this linear elastic perfectly plastic model. I here added the parameters to calibrate the model, that is the elastic modulus, the Poisson ratio, I will talk a bit about that on the next slide, the friction angle, cohesion, and the latency, angle of the latency. The cohesion and the angle of the latency are kept to 0 in this simulation. On the next slide, I vary Poisson ratio. I increase the Poisson ratio for this response of a conventional trained triaxial test. And for this conventional trained triaxial test, we can see that a change in Poisson ratio only affects the volumetric response in that case. For other element tests with kinematic constraints as the odometric compression test, or for example, a plane strain biaxial compression test, the Poisson ratio does affect the stress path, And I recently uploaded some animations related to the influence of the Poisson ratio on the web page to illustrate the effect on stress path. There is a bit more related to linear elastic perfectly plastic models on a web page. I will now present models related to critical state soil mechanics. That is the modified CAM-CLAY model, or I chose, there are a lot related to critical state soil mechanics. I chose the modified CAM-CLAY model and clay hypoplasticity. On the left, I again show PQ plane with the red line, that is the so-called critical state line, and the blue line here is the hydrostatic axis. On the right side, you can see the void ratio mean effective stress plane, again with the critical state line in that plot and a so-called normal compression line to define normally consolidated states. If a constitutive model includes the void ratio or an overconsolidation ratio as an additional state variable, that makes it possible to distinguish between loose and dense or states or different overconsolidation ratios. In both models, there is a stress-dependent critical void ratio in the void ratio mean effective stress plane in order to distinguish between loose and dense soil, or for clays between normally too slightly and highly overconsolidated clays. These points are endpoints of undrained, here in 1+ void ratio mean effective stress plane, endpoints of undrained Drexel tests of normally and overconsolidated reconstituted wheel clay samples. And they can be approximated by this red line to describe the critical void ratio. And if we plot this line and the experiments in a logarithmic plot, the critical void ratio can be well approximated by a straight line for clays. And this critical state line is assumed to be parallel with the normal compression line, which is also included in clay hypoplasticity and in the modified CAM-CLAY model. The modified CAM-CLAY model is an elastoplastic hardening model assuming so-called associated flow. I here show again the critical state line in PQ plane. Below, I show void ratio mean effective stress plane with the critical state line in this plot to distinguish between slightly overconsolidated and highly overconsolidated states. And I show the normal compression line. Here above right, the deviatoric stress, deviatoric strain response will appear. And below, I will show the volumetric response in void ratio deviatoric strain plane. I will now show the simulation of an conventional drain Drexel test of an initially normally consolidated clay sample. Normally consolidated means that the current mean effective stress is equal to the pre-consolidation pressure. And that implies that the initial state is on the so-called normal compression line. And here on the right, the critical state line in PQ plane can be described with the equation above. The critical state line in void ratio mean effective stress plane with the equation below, and in the logarithmic plot parallel to that is the normal compression line. I start the animation and we can see hardening of the yield surface. We can see the yield surface grow, and we can see that the yield surface has an elliptic shape. I wrote the equation here on the right side. Associated flow implies that the plastic strain increments are perpendicular to the yield surface. And as I continue the test, and we can see that the volumetric plastic strain increment decreases compared with the deviatoric strain increment. And as we further approach critical state, the critical state lines in both planes, we can see that we just have distortional strain eventually at constant void ratio. And the stress strain response is typically for normally consolidated clay as we approach critical state. On the next slide, I again show the same planes. I now show an animation of an initially highly overconsolidated clay. Highly overconsolidated means that there has been a higher pre-consolidation pressure, which defines the size of the yield locus, than the current initial mean effective stress. And highly overconsolidated clay implies that the current void ratio is smaller than the critical void ratio. I again start the animation, and until the yield locus is reached, the behavior is elastic, and we can exceed the critical state line here and get higher stress ratios than the critical stress ratio. And as we reach the yield locus, it shrinks until critical state is reached. And here on the so-called dry side of critical state, the plastic volumetric strain increment points to the left. That means that the sample has to dilate in order to reach critical state. And again, the volumetric strain increment vanishes, and we just have distortional strain until we reach, or as soon as we reach critical state. What we can see here is that we have a peak state with subsequent softening. Yes. On the web page, you can also find animations and simulations of with a modified ChemClay model for undrained compression test. On this slide, I summarize the parameters for the modified ChemClay model. That is the critical friction angle to define the slope of the critical state line in PQ plane, the ordinate intercept and the slope of the normal compression line, a slope of an unloading line, and a shear stiffness. I talked a bit about this elliptic yield surface here in stress plane. If we have a look in principal stress space, I can show how the yield locus of the modified ChemClay model would look in principal stress space. And in the deviatoric plane, in that case, Drucker-Prager is assumed. That brings me to visualizations related to clay hypoplasticity, which includes a very similar concepts as the modified ChemClay model. It's just the mathematics behind it differ a lot. Above left, I again show PQ plane with the critical state line. I will here talk again about conventional drain triaxial tests, and I already plotted the response of an initially normally consolidated sample. To the right, I show the stress strain response, which looks very similar to the response of the modified ChemClay model for the normally consolidated sample. Here I added the stress ratio with over the deviatoric strain, and below I again added the void ratio mean effective stress plane with the normal compression line and the critical state line, and the volumetric response described through the void ratio with ongoing deviatoric strain. The initial state is indicated with a circle, and the final state is indicated with a bullet. I will now show, keep the void ratio constant for all the simulations I will show, and I will show the influence of the initial stress. I will increase the overconsolidation ratio by decreasing the mean effective stress, and by keeping the void ratio constant. This is the response of an initially slightly overconsolidated clay. I increase the initial stress state a bit. That results in a lower strength. We get the same critical stress ratio and contractant behavior throughout the whole test. I further increase the overconsolidation ratio by decreasing mean effective stress. And as soon as the initial state is below the critical state line, the initial state is highly overconsolidated. That means in the volumetric response, we get dilatant behavior in order to reach the critical state line. We can see in the stress strain response a peak state and subsequent softening. And we can see that the stress path exceeds the critical state line here in PQ plane. And that's what we also can see here on the right, that the stress ratio exceeds the critical stress ratio. It is important to include the void ratio as a state variable for stress dilatancy effects under shearing. And the normally and slightly overconsolidated samples, they contract, and the highly overconsolidated samples behave dilatant until they reach critical state. On this slide, I again show simulations of consolidated train triaxial tests. This is basically what we just saw before, but with an initially normally consolidated sample. This time, I will increase the overconsolidation ratio by decreasing the void ratio and by keeping the initial mean effective stress. And that implies that for the normally and slightly overconsolidated response, the stress path will overlap, and the other curves look quite similar. And as soon as the initial state is highly overconsolidated, we get the typical response of a highly overconsolidated clay. That means that the stress path again exceeds the critical state line. The stress strain curves have peak states, and the stress ratio exceeds the critical stress ratio. That means that the mobilized friction angle is higher than the critical friction angle. I will now show the hypoplastic response of undrained compression tests. As the volume is kept constant in the test, I skipped, before I showed here the void ratio deviatoric strain plane. As the void ratio is constant in this test, I exchanged it with the bore pressure development, and all the other planes are the same as for the trained response. This dotted line indicates the total stress path, and I show the effective stress path here of an initially normally consolidated clay. The volume is kept constant and approaches the critical state line in both planes, and we get an increase in pore pressure throughout the whole test. In that case, I again show the influence of initial density. I keep the initial stress level fixed and just vary the void ratio. I reduce the void ratio, and with that, I increase the overconsolidation ratio. And we can see keeping the initial mean effective stress and just decreasing the void ratio highly affects undrained shear strength. We can also see that again, the highly overconsolidated clay exceeds the critical state line. The stress ratio exceeds the critical stress ratio, and peak friction angles are higher than the critical friction angle. On the next slide, I again show simulations of consolidated undrained triaxial tests. I again start with a normally consolidated response. And this time I increase the overconsolidation ratio by decreasing the initial mean effective stress. This time I will keep the initial void ratio constant for all the tests. And we can see here that independent of, with a constant void ratio in the framework of critical state soil mechanics, critical strength depends on the initial void ratio, but not on the initial mean effective stress if the void ratio is kept constant in all simulations. However, again, the initially highly overconsolidated samples can exceed the critical state line, and higher stress ratios than the critical stress ratio can be reached. At this slide, I show the parameters which are necessary to calibrate hypoplasticity. I sometimes have heard rumors that hypoplasticity or the parameters of hypoplasticity are not related to physical quantities, and this is certainly not true. We again need the ordinate intercept and slope of the normal compression line in a logarithmic plane, the slope of an unloading line, the critical friction angle to define the slope of the critical state line, and an additional parameter to control the ratio of shear and bulk modulus. And what you can also see here compared to the modified Kempler model is that the response is smooth. Yes. On the next slide, I show a 3D view of the so-called asymptotic state boundary surface of clay hypoplasticity. That is a bounding surface to limit certain feasible states in clay hypoplasticity. In the middle, I show PQ plane, what we saw before with a critical state line and normal compression line, and indicating the bounding surface to bound feasible states. And on the right, I show void ratio mean effective stress plane, again with the normal compression line and again with the critical state line. I now start the animation and stop it when the lines are projected in PQ plane. And this animation, just wait a bit. And this animation should help to show that the critical state line and normal compression lines, how they can be interpreted as three-dimensional lines in PQ void ratio plane. And now in the PQ projection, we basically or exactly see what we can see here in the middle. We see in red critical state line, in blue the normal compression line, and the bounding surface. And as I further rotate this surface into void ratio mean effective stress plane, we will eventually just see what we see here to the right, the normal the PQ plane, the void ratio mean effective stress plane, what we're used to. And that's what we can see here. And again, it might be of interest for some of you to not only look at the animation, but to rotate this surface by your own. And you can do that whenever you want and look into void ratio mean effective stress plane. You can have a look at PQ plane or whatever you're interested. And before I showed the bounding surface of the modified Kempler model in principal stress space, here I show the bounding surface of clay hypoplasticity in principal stress space. And as I talked about Matsuoka Nakai before, the shape of the, for example, critical stress locus of the bounding surface has the shape of the Matsuoka Nakai failure surface. I will now talk a bit more about the project and which material can be used. you find those interactive graphics which are included in web pages. They are included in a sub page of soil models. And you can directly download the visualizations. You can download the PDF or a GIF animation. I will explain that here. The advantage of the PDF animation is that you can take a break if you want. You can increase speed, and of course you can decrease speed, and yeah. And you cannot do that with a GIF animation. Therefore, it might be of interest to use the PDF animations, and you can find them on a web page. And you can also find all slides of an animation as PDF. And to have all slides of an animation as PDF makes it easy for you to pick the slides you want to use. If you just want to use the last slide, you just pick the last slide and use it, and don't necessarily have to take all of them. Where to find these animations? You can find all the visualizations on a sub-page of the page soil models. There are a lot of further useful things on the soil models web page. Probably most of you know the page. For those who don't, it's definitely worth to have a look. For example, there is a calibration tool. If you have laboratory test data, you can upload your test data and you can calibrate different constitutive models like the modified ChemCl model or hypoplastic model. And it's, for some pages you need an account, but it's free. And talking about soil models, I want to thank David Machine from Prague for providing this subpage and also for supporting me on this web page. In addition, you can find, for example, MATLAB scripts to calculate and plot 3D surfaces of Matsuoka Nakai, Mokolomb, and Foca Braga. That brings me to the summary and to the benefit of the animations. There is a personal benefit of the animations, which is that I really enjoy doing this. And the other benefits are more related to the understanding. Animations enable to create a figure as a process, and to see a process can help to understand things. And this process can even be followed in several images at the same time. And in an animation, a moving image helps to get the right focus. For example, if the yield surface of the modified ChemCl model grows, it will make you watch the yield surface. However, the visualizations certainly do not replace all the other aspects of learning and teaching soil models. As I mentioned at the beginning, that is studying the equation, doing computations, having discussions, going to university or courses or reading books. But I hope they can facilitate teaching, and I hope that they also can facilitate learning and understanding different concepts related to soil constitutive modeling. That brings me to the last page, to the acknowledgement. It was a bit more than a year ago that I started sharing my visualizations on social media. And some people liked them and asked if they can use the visualizations for teaching. And that was, in fact, the idea for the project, that I continue with what I like and that others and I can use them for teaching and learning. And in fact, I got this idea through other geotechnical engineers on Twitter. And I want to thank them and, of course, everybody else for the ongoing interest in this project. And in addition, I want to thank the University of Innsbruck for funding the project. And of course, the Mexican Society of Geotechnical Engineering for inviting me today. And last but not least, I want to thank you for staying and thank you for your attention. And I'm open for questions, discussions and further input. Thank you.
Thanks a lot, Dr. Medicus. Now we're going to start our session of questions and answers. I will going to read the questions in Spanish. Voy a leer las preguntas en español y nuestro traductor realizará la...
I will read the questions in English and our interpreter will convey that into English. Rafael Ortiz is asking, excellent project. I think that as part of the teaching of these models, we could include them how the failure of a soil probe tube, and thus we can link the results of triaxial tests with the construction of a system.
You mean that I go a step further and from the constitutive models to how this is in an application, or was that a question, Ricardo? Maybe it's in the chat as well.
Sí, doctora, a eso se refiere.
Yes, doctor, that is the meaning of the question, how we can use or how we could complement your project with the failures in the test probes as it moves in the effort paths.
You mean as an additional project, or as I think like my intention of this project is to make people be aware of what different models can capture and what others cannot capture. And for example, if the stiffness, the stress-dependent stiffness is important for your application, then you rather use a constitutive model which can describe the stress-dependent stiffness, that's the intention of my work here, and to maybe get a bit lose the fear, for example, of these tensorial equations that are often mentioned related to hypoplasticity. And yeah, to make you choose the appropriate model for your application.
Muy bien. Aquí nuevamente Rafael
Okay,
Ortiz.
thank you. Rafael Ortiz, again, he makes a comment and he's clarifying your question, and he is doing that in English.
The answer of Rafael Ortiz. He asked, the idea is to link how can the triaxial test relates to the behavior shown in the model.
In the model or in the application? In the model. The triaxial test is just one possible response of the model. There are, of course, many other possibilities of a response of a model. But this is it's one possible response, and if you're interested in failure predictions, slope stability analysis, or things like or strength reduction analysis, then the triaxial compression or extension or test is maybe more interesting than an odometric compression test. But I'm not quite sure if I completely got your question.
Okay, we're going to, I'm going to read the question of Dr. Paul Garnica. Can we use these visualization tools for our own test data?
You can use the calibration tool for your own test data because you can upload your own test data. You can so far I just uploaded scripts for the 3 failure surfaces I showed. There you certainly can adjust, for example, the critical friction angle for your test data. Apart from that, I have not uploaded the scripts. I just uploaded the animations. But if you think you can use them for your data, just write an email and we can see what you need for your test data. Maybe if you give an example how you could use this for your data, then this could certainly work.
Okay, excellent, Doctor. Also, Dr. Paul Garnica asked, can cyclic test be displayed using these visualization tools?
Yeah, in fact, we recently did that. I didn't show an animation of cyclic response, but we just have a journal article under review, and we also added animations to that. And there we compared the different small strain and cyclic approaches, and I will also link them to the webpage to describe the cyclic response. Yes,
Okay.
This is the plan, and up next month.
Oh, excellent. That will be interesting. Ruben Flores asked, a query knows of some geotechnical modeling for soft soils and its applications in embankments.
This question is.
Yes, this is a little confusing.
A query knows.
Yes.
I don't really get it. This like the models for soft soils as the modified ChemCanol or clay hypoplasticity. These are models for soft soils and especially for clay hypoplasticity with a lot of extensions as natural soil, anisotropy, small strain approaches, strength, stiffness, anisotropy, and things like that. You can, in fact, also find all those extensions of the models on this soil models web page. And then it depends on your application, which extension of clay hypoplasticity you will or you can use.
Okay, also Gabriel Colorado asked, have you implemented the visualization with the students in class? If so, have seen any improvement on the students?
I have used this in my class, and I also have a cooperation with 2 other researchers. They also use it. It's always hard to, how can you measure an improvement of students? It's hard to measure. We even will do a query soon about this project, one for students and one for lecturers. I think if students like the animations and play around a bit themselves, then I count this as success because this might increase their interest. But I think it's hard to measure from 30 students this year or last year an improvement. But if you have an idea of, because we discussed it, in fact, a lot, how can you measure an improvement due to this project, for example? I'm not sure if grades are the right measurements, but Gabriel, if you have an idea how to measure the improvements, I'm happy if you could share it with me.
Yes, maybe ask them, no? Okay, in our chat also we have a question. Nathan asked, excellent presentation. Will you pursue something similar to help visualize stress states using bounding surface plasticity?
Yes, this is good you mentioned that question, because I was asked for a cooperation of a bounding surface plasticity, and I almost forgot about that, and I will come back to this person, and we will do that, and I will upload some this autumn. Or at least it's the plan if I have time, but I haven't yet done that.
Okay, excellent.
But thank you. I take a note because I I should have done that some time ago
Okay.
already. Thank you.
Okay, Juan Manuel Villagrán asked in Spanish. Gracias por la ponencia, doctora Gertrude.
Thank you for
Regularmente
your presentation, Dr. Gertrude. Regularly,
tenemos que quedarnos con los representado en 2D en un
need
pizarrón
to
de
keep
clases.
what is represented in the 2D dimension on a blackboard in a schoolroom.
Y estas representaciones
And these
3D
3D representations
facilitan el entendimiento y aún
make
más la
us
comprensión de los
easier to
modelos.
understand the models a little bit further.
Oh, thank you. Yeah, that's good. I can also remember as a student that for example, the critical state line or normal compression line as 3-dimensional lines, I think, yeah, it can help to use this interactive plot and rotate it yourself to really understand the projections. And yeah, that's good if it helps. And in the handout, because there are some other useful tools, and I in the handout after the at the last page, I added some further useful information and other examples that can be used for visualizations of or teaching or understanding soil constitutive modeling. That is the calibration tool I talked about. And also there is another interactive visualization of the original CAMCLA model by another researcher called Anil Yilnis. And you can, if you download the handout, you can check that out. And I also saw the next question related to books, and there is a YouTube channel by Nicolas Espinosa I can highly recommend in order to get detailed explanations to all or to a similar topic. So there are a lot of other very useful tools available.
Excellent. Flavio Rojeiro.
Excellent, Flavio Rojeiro.
That's a great project, not only because you can have a better perception of the model performance, but because you can have the opportunity to choose the best model for the situation that you are studying. Have you used it to visualize the influence of suction in strength for unsaturated soils?
I haven't done that, and I fear this would be definitely really interesting because this is a very important topic, but I fear I won't have enough time. The reality is I make one animation and I have the idea for 2 more, and so I have a kind of exponential growth of ideas. And but the more time I spend on the project, the more I realized how much time I could spend on the project. And it's definitely, I fear I won't make this within this project, but I take a note anyway, because I have a long to-do list, and who knows what the future brings. Yeah, thank you for the input.
Okay, also here in our chat, I will read it in Spanish. La modelación hecha con la teoría de
The
Moore-Coulomb
modeling made with the Moore-Coulomb theory,
la considera que es menos
you
rigurosa
consider that it is less rigorous
que la desarrollada con la teoría de
than
Matsuoka
that
Nakai.
developed with the methodology of Matsuoka Nakai?
¿O cuál de ellas considera que
Or
arroja
which of
mejores
them
resultados?
do you think that yield better results?
From the true triaxial or biaxial plane strain biaxial test experiments, Matsuoka Nakai is reported to give more realistic results than Moore-Coulomb. Yeah.
Excellent. Yes, of course. Okay, another one. Great presentation. Is Dawood? It says great presentation. Question: is the flow rule on the deviatoric plane for the hypoplastic model using Matsuoka Nakai failure criterion associated or non-associated?
It is in a deviatoric plane hypoplastic model. It is in alignment. It is, if you translate it into elastoplastic model, it is associated. Yes.
Excellent. Okay. Here in the gelling dye, says in English, Dr. Medicus, could you please recommend some books related to constitutive models? Just to name a few.
If you write an email, I can mention the whole books. I would recommend. I have them here. It's for modeling. I think you can see it. It's geotechnical modeling from David Merwood. That's how I got into the topic, and it's also soil behavior and critical state soil mechanics from David Merwood. If I would suggest two books, then I would suggest those two.
Mm-hmm. Okay, here in our chat, Felix Sosa asked in Spanish.
But maybe to mention, like what that would you ask, it's just associated in the deviatoric plane, not in PQ plane, if that.
Okay.
Yeah, because that's, I think, important. And
Okay, well, okay, Felix Sosa asked in Spanish. ¿Cree usted que valdría la pena implementar la realidad?
Do you think that it would be worth to expand the increase or augmented reality?
Y o realidad virtual
and
para
or
este tipo de
virtual
temas?
reality for this type of subjects?
Yeah, do you have some more specific ideas for that? But it's definitely worth thinking about that. And yeah.
Okay. Excellent. Okay, Pastor also asked the question in Spanish. ¿Podría mencionar,
Could you please mention
cuál podría ser el impacto de
which could
considerar
be the impact to consider
o no la hipoplasticidad en
or
túneles
not
excavados
the hypoplasticity in excavated tunnels
en suelos blandos o en
in
cimentaciones sobre
soft
suelos
soils
blandos?
or in cementations on soft soils?
Like how hypoplasticity could contribute or like, I don't know if there's an extension of hypoplasticity for cemented soils. There might be an extension for that, but I have never been dealing with extensions for cemented soils. Was the question related if how the performance is?
Yes, more or less the performance of these tunnels or cementation.
I think the David Machine, he published some predictions related to tunneling, and again it also depends on what you build, but it also depends on the soil, if it includes anisotropy, if it is important to consider the small strain response. But I think he did a class A prediction of a tunnel with clay hypoplasticity and a small strain extension. But yeah, it's definitely possible and definitely has potential to do these calculations with clay hypoplasticity.
Yes, and model. Also, Pastor asked if you can give us some course of this use of these models. A short course here in the Mexican society.
It depends a bit on my time, and we can discuss that afterwards. I really like to do these things, but I have to finish a lot of project within the next months, and I don't know yet where I will be afterwards. But basically, I'm interested in doing these things, so we can discuss that if you want. Thank you.
Excellent. Maybe we can talk later for that.
Yeah, perfect.
Thank you. Thanks a lot. And that's all, Dr. Medicus. The other participations is the greetings for your participation and your presentation, and that's all.
Yeah, thank you. And I'm aware that this was a lot of input for this hour, but it was also to get an overview. If you pop over hypoplasticity in half a year, then I can check this webpage and can have a deeper look. And maybe there are some lecturers also sitting here, and then they can get an overview what they can use for their courses. And if you have further question, yeah, just write an email and we get in touch.
Thanks a lot.
Thank you. Yeah, thank you for inviting me.
Don't go. We will going to give you a recognition. Roberto Velar, please.
No tengo ahorita. ¿Tú me
We
vas a
can
ayudar con
hear
la-
you, Roberto.
I do not have,
Bueno, ¿me escuchan?
can you hear me now?
¿Me escuchas?
Can you hear me?
Sí.
Yes, yes.
Okay. I have had some issues with this updatings and my computer. I offer an apology because of that. Gertrude Medicus, sorry.
Oh, don't worry.
With my PC, but for the Mexican Society for Geotechnical Engineering, is very, very honored that you be with us.
Yeah, thank
Thank you very much. Your lecture really is very didactic and also explain us a lot of things that we have to interpret in the future. So I'm very, very glad to meet you.
Thank you. Same for me. Thank you.
Ricardo, I don't have in my phone the recognition. So
Okay.
can you?
Yes, please, Miguel Manica, can you support us to give this recognition, please? Thank you, Miguel.
Yes, sure. Well, thank you, Doctor. It was a very nice presentation. I can assure you that I'll be using your visualization tools in my class.
Yeah, thank
So-
you. Perfect.
We would like to give you this certificate of recognition. I'm going to read it very, very fast. So the Mexican Society for Geotechnical Engineering present this certificate of recognition to Gertrude Medicus for her distinguished participation in the lecture, The Use of Visualization for Teaching Soil Constitutive Models in Mexico City, the 16th of August, 2021, and it's signed by our President, Roberto Avelar, and our Vice President, Ricardo Ortiz Hermosillo, who was also the one that coordinate this event. And we will be sending you this by email. So thank you very much.
Yeah, thank you very much. Thank you.
Thank you, Dr. Medicus, and that's all.
Yeah,
Thanks a lot.
talk to you. Bye. Have a nice
Good
day.
day. Good afternoon, everybody.
Yeah, same for you. Bye.
Bye.
Bye to
Thank you.
everybody.